Chapter 1.2.6 Caching, the Invisible Performance Layer. When you first hear the word caching, you probably picture something small, a minor detail, an optimization you sprinkle on top once the real system is already built. But in real cloud systems, caching isn't decoration. Caching is survival. It's the invisible performance layer that sits quietly between your application and your database, answering one very practical, very human question. Do we really need to ask the database this again? When we say cache, we're not talking about something abstract or magical. A cache is simply memory, usually running on separate servers or services, designed to answer requests faster than a database ever could. It doesn't replace the database. It stands in front of it, handling the questions that are asked over and over again. Because databases are exceptional at one thing: preserving truth. They remember. They protect what must never be wrong. But they are not fast. Compared to memory, databases are slow. And memory, even though it forgets everything when the power goes out, is unbelievably fast. This isn't because databases are poorly built, it's because they do more work. They validate data, maintain indexes, enforce consistency, and often write to disk. Memory skips most of that, and speed is the result. So caching is the compromise you make with reality. You accept that not everything needs to be perfectly fresh every millisecond. And in exchange, your system becomes fast, calm, and resilient under pressure. When you introduce caching, three things happen almost immediately. Responses get faster, database load drops, and the entire system becomes calmer during traffic spikes. And in the cloud, calm isn't a luxury. Calm is the difference between we survived the traffic and we had an incident. To really feel what caching does, imagine a simple scene. A user opens your app and taps Profile. Your backend needs to return the user's name, avatar, and basic settings. If you go straight to the database every single time, the flow is predictable. The request comes in, your service asks the database looks up the data, responds, and you return it to the user. It works, and for low traffic, it's fine. But it repeats endlessly, and it's expensive. Now let's replay that same scene with caching in place. The first time that profile is requested, the cache is empty. Nothing is stored yet. This is called a cache miss. So the service goes to the database, fetches the profile, returns it to the user, and then quietly stores a copy of that data in memory. This copy is usually stored under a simple key, like a label, that represents the request. Next time the same request arrives, the system looks for that label in memory first, instead of rebuilding the answer from scratch. Nothing special happens, the user doesn't notice. Now the second request arrives, same user, same profile. This time the cache already has the data. This is a cache hit, and the moment you get a cache hit, the system behaves like it's discovered a shortcut through the city. No database call, no waiting, just an instant response. That's the entire mental model. A cache miss means you fetch from the database and store the result for later. A cache hit means you serve directly from memory. Once you hear it that way, caching stops being mysterious. It becomes a habit, a reflex. But there's something subtle here that many people miss. Not all caches feel the same. Imagine you just deployed your system. Everything starts fresh. The cache is completely empty. Every request misses. Every request goes to the database. This is called a cold cache. Cold caches often appear after deployments, restarts, or scaling events. Nothing is wrong, but everything is suddenly expensive again. This is why the first minutes after a deployment are often the most fragile. Cold caches are slow, noisy, and database heavy. They aren't broken, they're just new. Now imagine the same system after a few minutes or hours of real traffic. The most frequently accessed data is already in memory. Profiles, configurations, popular items. Now most requests are hits. This is a warm cache. And when a cache is warm, the system suddenly feels alive. Responses are fast, the database breathes easier, everything flows. Understanding cold versus warm cache behavior is critical because many systems fail not under steady load, but during restarts, deployments, or traffic bursts. When the cache suddenly becomes cold again, Once caching becomes part of your system, the next question naturally appears. Which cache do you use? Before we even compare names, let's slow down and make one thing very clear. Redis and Memcached are not ideas, and they are not pieces of code you sprinkle into your application. They are real programs, services, that you run alongside your system in the same way you run a database server. When you build a system, you don't build just one thing. You build several components that work together. You have your application, which handles requests and business logic. You have your database, which stores truth. And then you add a cache service, Redis or Memcached, as a separate running process whose only job is to answer repeated questions quickly. Your application does not become Redis or Memcached. It doesn't absorb them, it talks to them, over the network just like it talks to a database. Every time your application needs some data, it follows a simple habit. Before walking all the way to the database vault, it turns to the cache service and asks, "Do you already have the answer to this?" If the cache says yes, the database is never touched. If the cache says no, only then does the application go to the database and remembers the answer for next time. Most engineers hear the same two names again and again, Redis and Memcached. They look similar on the surface. Both store key value data in memory. Both reduce database load. Both make systems faster. But they have very different personalities. Redis is the Swiss Army knife. It lives in memory, so it's fast, but it can also persist data to disk if you configure it to. More importantly, Redis isn't limited to simple values. It gives you richer structures that let you model real application behavior. Queues, feeds, leaderboards, session stores, rate limiters. Redis doesn't just store data, it helps shape how data flows through your system. This flexibility is powerful, but it can also be dangerous. Redis can persist data, but it is not meant to replace a database. Treating a cache like a source of truth is one of the most common architectural mistakes. Memcached, on the other hand, is the pure sprinter. It's designed for one thing: to be as fast and simple as possible. It's distributed by nature, meaning you can easily add nodes to scale out, but it doesn't have Redis's data persistence or rich data types. It's a straightforward high-performance cache and nothing more. One feature that quietly changes how you think about data is TTL, time to live. TTL means cached data can expire automatically. You don't need to remember to clean it up. The cache itself decides when data has become stale, and this is where caching starts to teach maturity. Imagine your application shows a product price. A user opens the product page. The price is €50. The page loads instantly because the price was cached. Perfect. Now, in the background, something changes. A promotion ends. The real price is now €60, but the cache still holds 50. So another user opens the page and sees the old price. The database is correct. The cache is simply behind reality. This moment isn't a bug, it's a lesson. Caching always forces you to answer one uncomfortable question: how wrong is acceptable, and for how long? Sometimes being slightly wrong is fine. View counters, likes, trending lists, analytics. If a number is off for 20 seconds, nobody's world collapses. Sometimes being wrong is not fine. Money, orders, inventory, ownership. Caching is never free performance. Caching is a trade-off. Speed in exchange for controlled staleness. TTL becomes your steering wheel. Short TTL means fresher data but more database load. Long TTL means faster responses but more stale data. TTL is not just about expiration, it's about limiting damage. Even when invalidation fails, TTL guarantees that wrong data cannot live forever. Even with basic caching, you're already thinking like an architect. But there's another quiet challenge hiding here. In real systems, you rarely have just one instance of your service. You have many, and each one may talk to the same cache, or sometimes each may hold its own local cache. This is where cache coherence problems appear. Cache coherence is what happens when multiple parts of your system hold different versions of what they believe is the same data. One instance thinks the value is 50, another already knows it's 60. Nothing is broken in isolation. But globally, reality becomes inconsistent. This inconsistency is not always a bug. It's often a consequence of choosing speed and availability over perfect synchronization. The key is knowing where that inconsistency is acceptable and where it is not. As systems scale horizontally, cache coherence becomes one of the hardest problems to reason about, because the system is now fast, distributed, and partially out of sync by design. And this is why caching decisions are never purely technical. They're philosophical. You're choosing where inconsistency is allowed to exist. There's another layer of caching most users never think about, but they feel it every day: client-side caching. Your browser caches images, scripts, and responses. CDNs cache content close to users around the world. This kind of caching happens before your request even reaches your backend. From the user's perspective, this is often the biggest performance win. If the request never reaches your servers, nothing downstream needs to work harder. Server-side caching, like Redis or Memcached, happens deeper in the system, between your services and your database. In real architectures, these layers stack: a browser cache, then a CDN cache, then a server-side cache, then the database. Each layer removes pressure from the one below it. When done well, requests barely reach the database at all. But caching also has sharp edges. One of the most dangerous is something called write amplification. This happens when poorly designed caching logic causes more writes than necessary. For example, updating cache entries too aggressively, writing to cache and database redundantly, or refreshing large cached objects when only a small piece changed. Instead of reducing load, the cache multiplies it. The system looks fast, but behind the scenes, it's working harder than before. This kind of hidden cost is dangerous because dashboards may look healthy. Latency drops, but infrastructure stress rises silently. This is why some teams learn the hard way that caching isn't just about reads, it's about disciplined writes. Now let's talk about the kind of failure that causes real outages: cache invalidation. There's an old saying in engineering that never gets old: caching is easy, invalidation is hard. Invalidation is deciding when cached data should stop being trusted. Expire too early and you lose performance. Expire too late and you serve wrong data. And under heavy load, this leads to one of the most painful phenomena in distributed systems: a cache stampede. A popular piece of data expires. Thousands of clients request it at the same time. They all miss simultaneously. They all rush the database together. Instead of smoothing traffic, the cache creates a spike. This is why mature systems randomize expiration times slightly, so not everything expires at once, or they allow only one worker to rebuild missing data while others wait briefly or serve a fallback. These aren't optimizations. They're survival techniques. In interviews, caching often sounds simple, but experienced interviewers aren't interested in definitions. They're interested in safety. They want to know if you measure hit ratios, if you watch eviction behavior, if you understand how caching fails, not just how it helps. A high hit ratio means most requests are answered by memory instead of the database. A falling hit ratio is often an early warning sign, long before users notice a problem. And the most mature answer always ends the same way: cache hot data, not everything. Because caching everything isn't smarter, it's riskier. There's also a financial dimension to all of this. Databases are expensive to scale. Repeated reads cost real money. Caching shifts that load into memory, which is often a cheaper way to buy performance. That's why managed cache services exist in the cloud. They remove operational pain, but they don't remove responsibility. You still decide what to cache, for how long, and how much staleness your users can tolerate. Once you understand caching at this level, you start seeing it everywhere. Requests arrive. The cache is checked, hits return instantly, misses fetch from the database and become cheaper next time. That simple loop is one of the reasons modern systems survive Black Friday traffic, viral spikes, election nights, and feature launches. Caching makes systems fast, but speed isn't always the final goal. Sometimes you need buffering, sometimes decoupling, sometimes work that happens later. And that's where message queues enter the picture, which is exactly where this story goes next. End of chapter 1.2.6.